On March 6, 2026, something extraordinary happened, something that could forever change our understanding of the universe. A groundbreaking paper was submitted to Nature, one of the most prestigious scientific journals on the planet. This wasn't a preprint or a mere conference presentation. It was the real deal, a peer-reviewed discovery that came from NASA's Goddard Space Flight Center. The object of focus? The James Webb Space Telescope, JWST, and the finding it revealed was nothing short of mind-blowing. Deep within the distant reaches of our solar system, a small and ancient object passed through our neighborhood, and it brought with it a discovery that has stunned scientists. This object is known as 3I, Atlas, and its composition has opened a whole new world of understanding. The revelation? The water inside 3I, Atlas, contains 10 times more deuterium, an isotope of hydrogen, than any comet ever measured in our solar system. To put it simply, the numbers are off the charts, 10 times higher than anything we've observed before. But these are not just numbers to glance over. These are critical measurements that stand far beyond anything previously discovered in the cosmos. And the best part? This measurement was no fluke. It was precise 12 standard deviations above the mean for all known protostars in the Milky Way. This is no rounding error. This discovery leads us to a very curious question. Where did this deuterium come from? After all, Venus, the only object in our solar system that has a comparable deuterium ratio, gained its heavy hydrogen through billions of years of atmospheric escape. But 3I, Atlas doesn't have an atmosphere. It is a ball of ice and rock, just 2.6 kilometers in diameter, and has been drifting through the vast expanse of interstellar space for far longer than the Earth has existed. So how could this object contain such an anomaly? To answer this, the paper suggests that 3I, Atlas, likely formed at temperatures below 30 degrees Kelvin, 30 degrees above absolute zero. And here's where it gets even more fascinating. It formed in a stellar system that was relatively poor in heavy elements, a system much older than our own. Around 10 to 12 billion years ago, when our sun was still in its infancy, 3I, Atlas, was already ancient. Its formation predates the solar system by billions of years, and the object just happened to pass through our solar system at a time when we had the perfect tools to measure its contents. Stay with me, because what follows will challenge everything we know about the universe and its origins. Now, let's take a step back and understand why this discovery is so significant. What is deuterium, and why does its abundance in 3I, Atlas, matter so much? Hydrogen is the simplest element in the universe, consisting of just one proton and one electron. It is also the most abundant element in the universe, making up about 75% of all ordinary matter. It's the fuel for stars and the foundation of everything, from the air we breathe to the water we drink. But deuterium is a variant of hydrogen. While it behaves chemically in the same way, deuterium has an additional neutron in its nucleus, making it twice as heavy as regular hydrogen. This extra neutron is what makes it so important in astrophysics. In the early universe, after the Big Bang, deuterium was created in a fixed ratio to regular hydrogen. About 1 in every 40,000 hydrogen atoms was deuterium. This primordial ratio was set during the Big Bang nucleosynthesis, the first minutes after the universe was born. But stars, as they go through their life cycle, gradually destroy deuterium, fusing it alongside regular hydrogen to produce heavier elements. Over time, stellar processing leads to the depletion of deuterium in the galaxy. This is where 3I, Atlas, comes into play. The deuterium ratio in water found in comets in our solar system typically ranges from 0.03% to 0.06%. This is higher than the deuterium levels in Earth's oceans, which sit at around 0.016%, but still within a range astronomers understand. The reason for this is cold chemistry. At extremely low temperatures, deuterium prefers to attach itself to water molecules, forming ice on the surfaces of dust grains in molecular clouds. The colder the environment, the higher the deuterium content. This is an established principle in astrochemistry. Now, when we look at the water in 3I, Atlas, measured by the JWST on December 22, 2025, we find something extraordinary, a deuterium ratio of 0.95%. Compare that to the 0.03% to 0.06% we find in solar system comets and the 0.06% in Earth's oceans, and it becomes clear just how unusual 3I Atlas is. This is an order of magnitude higher than anything we've ever observed. This is not just a slight enrichment. This is an extreme anomaly, 12 standard deviations above the mean for the broader stellar population in the Milky Way. The paper itself describes this as a composition unlike any solar system body, and when we break that down, it's clear we've never seen anything like this before. But what does this 0.95% deuterium ratio mean for the formation temperature of 3I Atlas? The relationship between deuterium ratios and formation temperature isn't perfect, but it does give us a very clear direction. Higher deuterium means colder formation temperatures. For context, water ice in solar system comets with a deuterium ratio of about 0.05% formed at temperatures between 20 to 30 Kelvin. These are already extraordinarily cold temperatures, but for 3I Atlas, the models suggest a formation temperature of less than 30 Kelvin, likely much colder. In fact, it formed in a region so cold that even carbon monoxide, another gas found in molecular clouds, begins to freeze out. In other words, 3I Atlas did not form in a proto-lunar disk around a star. It formed in the coldest regions of a dense molecular cloud during the prestellar phase before any stars had ignited in the area. This is the coldest, earliest phase of star formation temperatures between 10 to 20 Kelvin with high densities that shield cosmic rays. This is the environment that produced 3I Atlas, and it has preserved a chemical memory of those conditions. The water ice in 3I Atlas holds a snapshot of the early galaxy untouched by thermal processing. It's a time capsule from a time long before the solar system formed, and then, after spending billions of years drifting through space, 3I Atlas passed by our solar system, carrying this memory from the past. It is now up to us to decode what it has to tell us about the universe's ancient origin. Stay with me as we explore even deeper implications, including the isotopic fingerprints of 3I Atlas and how they open up more questions about the early Milky Way and the formation of our solar system. Now, let's delve into what these measurements mean in terms of the chemical composition of 3I Atlas. The deuterium ratio we measured tells us a lot about the conditions in which the object formed. But it's not just the deuterium we need to focus on. There's also the carbon isotope ratios, and they too tell a fascinating story about the object's past. In any galaxy, carbon comes in two stable isotopes, carbon 1,2 and carbon 1,3. Carbon 1,2 has 6 neutrons, while carbon 1,3 has 7. The ratio of these two isotopes, 12C to 13C, is used as a clock to measure the chemical evolution of a galaxy. Stars produce more 13C as they age and eventually die, releasing it back into the interstellar medium. In our own solar system, the 12C, 13C ratio is about 89. However, in solar system comets, this ratio ranges from roughly 90 to 120. In nearby interstellar molecular clouds, it's between 60 and 80. This reflects the evolution of the Milky Way. The more 13C, the more stellar activity the galaxy has undergone. But 3I, Atlas's carbon isotopic ratio, is far higher than what we see in solar system bodies, at around 141 to 191 for CO2 and 123 to 172 for CO. This ratio points to an earlier epoch in the galaxy's history, a time when there had been fewer generations of stars and less enrichment of heavier elements. In other words, 3I, Atlas, formed in a part of the galaxy that was younger, with a lower metallicity, a metal-poor environment. This is a significant piece of the puzzle because it provides strong evidence that 3I, Atlas's parent star system, formed during a time when the galaxy was still in its early stages of evolution. This discovery is like finding a fossil from the birth of the Milky Way, preserved in an object that has now traveled across the galaxy, carrying with it the memory of a very different time. It's a snapshot of the early universe when the chemical makeup of the galaxy was vastly different from what we see today. But let's dig deeper into what the metal-poor environment means. When we talk about metals in astronomy, we're not referring to the elements like gold or iron that you might think of in everyday life. In astronomical terms, metals are anything heavier than helium, carbon, nitrogen, oxygen, and so on. After the Big Bang, the universe started almost entirely with hydrogen and helium. The heavier elements that we associate with life and planets were formed inside stars, released into the universe when those stars died, and then recycled into new generations of stars and planets. A metal-poor environment means that fewer stars had formed and died, meaning there were fewer heavy elements available to enrich the interstellar medium. This environment is indicative of an earlier stage in the galaxy's life, a time when fewer metals were present. This makes 3I, Atlas, a truly unique object. Its chemical composition and isotopic ratios reflect a galaxy that had not yet gone through the cycles of star, birth, and death that would later produce the rich metallic environment we see today. Its formation in such a metal-poor environment gives us a glimpse into the conditions that existed in the early Milky Way, long before the Earth was even formed. The implications of this discovery are profound. For starters, 3I, Atlas carries with it the potential to answer many questions about the early history of the galaxy. But there's another aspect of this discovery that could potentially change the course of astronomy. We now know that 3I, Atlas, is not just a comet from another stellar system, it's a physical sample of the early galaxy itself, a sample that has been preserved in the ice and molecules it carries with it. And what's even more exciting is that this object has given us a new way to measure the early Milky Way. It's as if we've discovered a new form of time travel, a way to study the chemical history of the galaxy through objects like 3I, Atlas, which preserve isotopic signatures from billions of years ago. This is not just a snapshot of a far-off comet, it's a tangible link to the distant past of our galaxy. So, what exactly does this mean for our understanding of the early universe? The evidence provided by 3I, Atlas, is clear. The chemical composition of the galaxy was very different during its early years. This object carries the fingerprint of a galaxy that was still young, cold, and metal-poor, and it formed in a pre-stellar core where temperatures were so low that even carbon monoxide was beginning to freeze. This level of coldness is not something we associate with the current Milky Way, where star formation and stellar evolution have enriched the interstellar medium with heavy elements. 3I, Atlas is a relic of an era when the galaxy was still in its infancy. One of the most exciting aspects of 3I, Atlas's discovery, is that it brings us closer to answering fundamental questions about the early conditions that led to the formation of our solar system. If we consider the deuterium-enriched water found in 3I, Atlas, it provides us with a chemical snapshot of how and where water might have been formed in the early stages of the galaxy. Water is crucial to the formation of planets and, of course, life itself. This could help us understand not only where our solar system's water came from, but also where other planetary systems might have found their water. The carbon isotopic ratios measured in 3I, Atlas also raise interesting possibilities about the history of organic chemistry in the galaxy. If organic molecules like methanol, HCN, and others found in 3I, Atlas, are similarly enriched with heavy isotopes, it could mean that the building blocks for life in the galaxy could have formed in environments vastly different from the conditions we're familiar with today. This could have implications for the study of astrobiology, as it suggests that the ingredients for life might be scattered throughout the galaxy in places we might never have expected. But there's more to this story. While 3I, Atlas is an exceptional object, it is by no means the only one of its kind. As we learn more about interstellar objects and how to study them, we will undoubtedly encounter more objects like 3I, Atlas, that carry similar chemical signatures. The discovery of 3I, Atlas opens the door to a new frontier in our understanding of the early Milky Way. And as we continue to measure and analyze more of these interstellar objects, we may uncover even more mysteries about the origins of our solar system and the broader galaxy. Now, with the Jupiter flyby of 3I, Atlas just around the corner, we have a unique opportunity to gather even more data before the object accelerates away from our solar system, never to be measured again. This is a rare, once-in-a-lifetime opportunity to study an object that has been traveling through interstellar space for billions of years. The window for studying 3I, Atlas, is closing fast, but what we've already learned from this remarkable object will continue to shape our understanding of the universe for years to come. As we prepare for the flyby, I want to hear your thoughts on this incredible discovery. What do you think the deuterium measurement tells us about the early Milky Way? Leave a comment below and let's discuss. Make sure you subscribe to follow the flyby in real time and share this with someone who thinks astronomy is just about pretty pictures of distant galaxies. This discovery is much more than that. It's a measurement of time itself. As we move closer to the Jupiter flyby, the excitement continues to build. The world's attention may be on the upcoming events, but few realize just how rare this moment is in the field of astronomy. 3I, Atlas isn't just any ordinary comet or asteroid. It's a cosmic time capsule that has preserved the chemical fingerprints of a galaxy in its infancy, one that formed billions of years ago when conditions were drastically different from what we see today. And now, after traveling across the vast expanse of interstellar space for more than 10 billion years, it's finally revealing its secrets to us. But the story doesn't end with the measurements we've already made. The potential for further discoveries is enormous. As 3I, Atlas moves closer to Jupiter, we are presented with a unique opportunity. The flyby could provide critical new data, especially when it comes to its outgassing behavior and how its composition reacts as it gets closer to the heat of the Sunday. The data gathered in these final moments will provide a wealth of information, not just about the object itself, but also about the broader processes that shape the early Milky Way. And yet, in just a few short weeks, the object will continue its journey toward the outer reaches of our solar system and eventually into deep interstellar space, beyond the reach of any instruments Once it passes Jupiter and accelerates away from the Sun, we will never have another chance to study 3I Atlas again. The precious window of opportunity is closing fast. However, what we've already learned has already reshaped our understanding of the galaxy's early days, and this discovery will continue to influence our research for years to come. One of the most fascinating aspects of this discovery is the concept of metallicity in astronomy. 3I Atlas is a relic from a time when the galaxy was still young, before the stars had released heavier elements like carbon, nitrogen, and oxygen into the interstellar medium. This low metallicity environment means that 3I Atlas contains far fewer heavy elements than objects from our own solar system, including comets and asteroids. This makes it an ideal object for studying the conditions that existed before the galaxy became enriched with heavy elements through successive generations of stars. With 3I Atlas, we've learned that the early galaxy was a much colder, less chemically rich place. It didn't have the same abundance of heavy elements that our solar system now possesses, and this has profound implications for our understanding of the formation of stars, planets, and even life. 3I Atlas is not just a comet, it's a witness to the past, a physical object that holds the memory of a time long before the Earth came into existence. The isotopic ratios of deuterium and carbon, the chemical signature of the object, and the environment it formed in are all pieces of the puzzle that help us understand the galaxy's early stages. But it's not just about the past, it's about the future, too. As we gather more data, the story of 3I Atlas will continue to unfold. This discovery could have implications for future space missions, the search for life beyond Earth, and our understanding of the very building blocks of the universe. As we near the end of this incredible journey, let's take a moment to reflect on just how much we've learned from 3I Atlas. The discovery of this object has fundamentally altered our understanding of the early Milky Way. We now know that the galaxy was not always the rich, metal-laden environment we see today. The low metallicity conditions under which 3I Atlas formed offer a rare glimpse into a time long before the solar system existed. It's a snapshot of a young galaxy still in its infancy, and the secrets it holds are more than just fascinating, they are essential to understanding how our universe evolved. But the story of 3I Atlas isn't just about science, it's also about the human quest for knowledge. The fact that we've been able to measure the chemical composition of an object that has been traveling through interstellar space for over 10 billion years is a testament to the incredible advances in technology and scientific collaboration that have taken place in recent years. The James Webb Space Telescope, one of humanity's most advanced instruments, has provided us with unprecedented views of the universe, and this discovery is just one example of the groundbreaking work it is capable of. As 3I Atlas makes its final approach to Jupiter and continues its journey beyond our solar system, we are left with more questions than answers. But that's the beauty of discovery. Every answer leads to new questions, and this is just the beginning. What we've learned from 3I Atlas is likely to shape the future of astronomy for years to come. The implications for our understanding of the early galaxy, the formation of stars and planets, and even the origins of life itself are profound. We may never again have the opportunity to study an object like 3I Atlas, but the knowledge we've gained will continue to inspire and guide future research. As we look to the stars, let's remember that every object, no matter how small, carries with it a story, one that we are just beginning to understand. And as we approach the flyby, the next chapter of this incredible journey is about to unfold. So, as we witness this extraordinary flyby, I encourage you to keep an eye on the data and stay tuned for updates. The science community is buzzing with excitement, and as the story of 3I Atlas unfolds, we will continue to uncover new revelations about the universe. This is just the beginning of an exciting new era of discovery. Make sure to hit that subscribe button and turn on notifications so you don't miss out on any updates. Share this with someone who loves exploring the mysteries of the universe and leave your thoughts in the comments below. What do you think 3I Atlas is trying to tell us about the early universe? Let's keep the conversation going. This is a journey we are all part of, and the best is yet to come.